We can also talk about triple integrals. Now that we've seen double integrals, I think you sort of get the idea. So I'll keep this video short and mainly focus on examples in the next videos. So if D is a closed and bounded region in space, and f x y z, or sorry, x y z is a function defined on D, we can define the integral of f over D, and we'll use the symbol dv for volume. Well, again, this will be the sum the limit of Riemann sums where we try to approximate, so try to partition D by boxes. And so the volume of the kth box will be product delta xk, delta yk, delta zk, and again, under reasonable conditions. So here we require that delta xk goes to 0. So as the number n of boxes goes to infinity, and also forcing all of the dimensions of these boxes to go to 0 for reasonable f, this will converge no matter how we choose the boxes, how we choose the partition, and we'll get the integral of f. So why would we do this? So first case is volume. So just as we could calculate the area of a region by integrating 1 over it, the volume, if we just integrate dv over d, or dx, dy, dz over d, so maybe I should say dv is dx, dy, dz, and then in the next unit or the next section, we'll see how to do versions of polar coordinates, or analogs of polar coordinates in 3 dimensions. Okay, so the volume of a region we can calculate just by integrating 1 over it. But if we try to integrate a general function over D, like we can do that, but what does this represent? So one answer you could say is, I guess you could say this represents a 4-dimensional hypervolume. But maybe that's sort of hard to visualize. Another, one application of 3D integrals that could be useful for understanding this is mass. So if we interpret f as a density function, so density has degrees, or like, let's say kilograms over meters cubed, or in general just like a weight over, mass over volume. So if D is the region occupied by some material, some physical material, and fxy gives the density at x, y, z, then instead of thinking of this as hypervolume, this will be the mass, so let me say, occupied by some object X, physical object X, so it has a density, then this integrating the density over the entire object will give us the mass of that object. And then finally, once again, if we can use this to define the average value of a function. So the average value of f on d is, we integrate f over d and divide that by the volume of d. Okay, so the next two videos, I'll work through a bunch of examples.